this session. Claessen is going to tell us about shrinking and showing functions.
Okay, thank you. Can you hear me? Yeah, great. Okay, so this is a function plural, but it's also a solution to a practical problem that many of you and also myself had when using QuickCheck. So I'm happy to be in a room with functional programmers that like pure functions and properties and these kind of things. And so here's a property of the well-known map and filter function that we all know and have seen before. And this is a nice property to have. So some people like to prove these kind of properties, but in this talk we're going to talk about testing these kind of properties. Okay, so we can use QuickCheck to test this property. And what it says is that for all functions f and predicates p, if you jump around map and filter, you get the same result, right? So let's do this. So I made a little, I prepared a little, wait a minute. So here it is. So we import QuickCheck, and we can write a property that expresses what I just said in the slide, and let's go and test it in GEC. And it passes the test. Oh, by the way, Simon, the property is false, and it defaults to unit, and that's why it's correct, because any list of units is equal to any list of units of the same length. So we have to, in order to use GHC, we have to also say what type we want to test this on. And there's a nice module in QuickCheck called poly, which allows you to use abstract types called A, B, and C that are basically natural numbers without any other functions and equality. So you can say, I expect this function to polymorphically hold for all A, but of course when we test it, we have to pick a particular A, and this is the A we're going to pick in that case. So if I'm going to restrict x's to be of type A, I'm going to test again. Okay, so now I test my property and it failed. It doesn't hold. It looked beautiful, but it was a wrong property. And here's the counterexample. If you take some kind of function f and some kind of function p, and then it has a list of one element in it, then that's it's wrong. So, how come it does this? Well, I'm using functions here, and a show instance of functions is just printing function on screen, so you can't look at the function. So QuickCheck is very nice. You can quantify over functions and it generates random functions, but you cannot look at the counterexamples. So what can we do? Well, we can do something. There's a function in QuickCheck called when_fail, which is executed when the property actually fails, and we can say, for example, print table of these functions, something like that. And I've already done that for you, so let's see how that might look here. So I say when_fail, print the table of f, use the arguments x's, and when_fail, print the table of p, using the arguments x's, and I've made a little helper function table that just constructs a list of pairs x and applying the function to x. Okay, so we can do that, and let's see what happens if we do that. Okay, so then we get falsified. We'll still get function because it can't show them. And we see the list x's that led to the counterexample. And we see the function table of f, and we see the function table of p. But of course we don't see the whole function table. We only see the function table that we chose to show. And in fact, these function tables are not enough to understand the property, that the property fails, because f takes 3 to 2. So if we map f over this list, we get the list of 2. And the predicate says that 3 is true, but in this function table, we don't know what the predicate says for 2. We would like to also see what the predicate says for 2. And we forgot to include that. So we have to do a little bit more work and think, when we print the table for p, we're not only interested in x's, we're also interested in map f(x)'s. Okay, and now finally we get to see the information that we want to see. So we see if we start with the list 4 and apply the function that takes 4 to 6, and the predicate that says 4 is false and 6 is true, then of course the property fails. Right? Okay, so a lot of manual work in finding the results. So what does this talk about? This talk is about avoiding this manual work and doing much of this automatically. And so instead of writing all this when_fail stuff, we write the property like this. So the only difference I made is that instead of quantifying directly over f and p, I'm quantifying over an object of a different type, fun AB. And And the implementation looks something like this. So I have a data type fun AB that has a constructor fun with the first argument, lots of administration hidden that you're not supposed to look at. And the second argument is the function that we want. So I'm quantifying over an object of this type and then just pattern matching out the function f and the predicate p and using that in my property here. So when I do that, then I get to see it's falsifiable. If I take the function that takes anything to 3, and then the predicate that takes 3 to false and anything else to true, and the list with 1 in it, then that's going to fail. And so that's easy to understand, and I didn't have to have any manual labor. So that's what this talk is about. Okay, I would like to show one more thing having to do with quantifying over functions. So many people think that when you quantify over a function, you generate some kind of random function, and that must already be some kind of finite table. But you cannot really, when you quantify randomly over functions in properties like this, you cannot really do that, because you never know beforehand what the function is going to be applied to. So look at this example property. It says that any property that Haskell 98 has also standard ML has. Right? For any P, if it holds for Haskell 98, it also holds for standard ML. Of course, that's not true, right? We know there's a counterexample. So let's figure out how to find the counterexample. So we're going to use this nice library. So we're not going to quantify over P, we're going to quantify over fun P. Okay, so it says that if you apply this to the predicate that gives false to standard ML and true to everything else, then it works. Of course, there's one other kind of characteristic counterexample. Hopefully we get it. Randomness, please help me here. Yes. So you can also say Haskell 98 goes to true and anything else goes to false, and that's also a counterexample. Of course, the quizzic didn't know beforehand we were going to apply the predicate to the strings Haskell 98 or standard ML. So when you generate a random function that's applied to an infinite type, you have to give it an infinite lookup table. And this is what QuickCheck actually does. And this is also the difficulty in then printing it out in the string, because we don't know which part of that lookup table we should print. Okay, so when you use QuickCheck, you really want to have the show function on the things you quantify over, because then you get feedback about why your property failed. There's also a shrinking function, which I sort of left implicit. And this talk is not really about shrinking in general, but the idea with shrinking is that when QuickCheck finds a counterexample, it applies a shrinking function to try to find smaller counterexamples. And that's really useful, because usually in random testing, when you get a counterexample, it contains a lot of junk. And shrinking helps in systematically trying to remove the junk until you get a locally smallest counterexample. I will tell you a little bit more about how shrinking works. But these two things you really want to have when you use random testing. Now, if you think about functions, I don't know how to show functions. And so when I tried to solve this problem, this is where I got stuck. And I didn't even dare to think about how to shrink functions, because that's even, my mind exploded when I was thinking about this. But it turns out that if you actually dare to think about shrinking, it helps when you have defined a shrinking function, it helps you with the show. Because what's happening is that shrinking takes the infinite function object to a finite object, and then show has a really easy time to actually show it on the screen. So that's what's going on. So if you want to take anything away from this talk, then this is the wisdom that the whole talk and the whole idea is based on. And it's actually quite trivial, but it helps us really a lot in this problem. So the wisdom that we're going to use is that in any terminating computation, if you pick any function, it's only going to be applied a finite number of times to a finite number of arguments. Right? Obviously, because otherwise it wouldn't terminate. It would be done if you wanted to apply it an infinite number of times. So how is this helping us? Well, of course, when we have a counterexample, QuickCheck found the counterexample false, that's a terminating computation, right? We've computed false. So now we know the function we're looking at has only been applied to a finite number of arguments. So let's figure out which those arguments are. And so we're going to treat this function as a partial function, although QuickCheck by default only generates total functions. But we're going to turn it into a partial function, and it doesn't matter because it's never going to be applied to the functions for which it's not defined. And then when we have found a final partial function, we're going to print it out. So our objective is to figure out what arguments is this function going to be applied to. And then a dark age in my life started. I felt the luring of the dark side. I thought, oh, of course, if we just could use some side effects. it would be very easy to figure out what the function would be applied to, right? So I came up with some code like this, and it looks ugly and it is ugly. So here's this fun object, right? It has two arguments, the actual function that we're going to try to match out, but it also has some administration, an IORF, that just remembers every argument we applied the function to and also the result. Okay? And then we have this wrap function that takes any function that we made and turns it into one of these ugly functions using the IO monad. And we just create a reference that is initially empty, and then we return log of f. And what does log of f do? Well, it unsafely modifies the ref by adding a pair to the list every time you apply the function. Right, so this is what you could do. Ooh. Yeah, indeed. Oh, I felt so horrible. I didn't dare to show this code to anybody, and I had nightmares about it. And so, but I thought if I just put it in the module and I never look at it, then it would just treat this, right? So, but what happened? Well, of course, I had to pay the price, right? So we added some parallelism features to QuickCheck, and then suddenly it breaks because IRFs in parallelism, and it's not going to work right. And even worse, it actually interfered very badly with shrinking. And you see my slide gets jumbled here? That's how jumbled the code became when I tried to fix all these things by making this code even more horrible. So then I really didn't try to dare to show this to anybody. So I admit I dabbled in unpureness, but I saw the light and I came up with a very nice solution. Okay, and it's all based around this function, this type that I call colon dash greater than, or a type of partial functions from A to B. So I'm going to define this type for you, and everything I'm going to solve this problem using this type. Okay, so this is the main type that I'm going to use. And I made a little picture of what kind of role this type plays and what the most important functions are in the type. So here's the new type, the type of partial functions from A to B. And here's the type of functions from A to B that we already know and use a lot. And it turns out that we can transform back and forth between normal functions and partial functions. And I call this function apply and this function build. So what's good about this type? Well, it has a concrete representation of functions. So we can do a lot more than just applying the function. We can, for example, shrink these partial functions to smaller partial functions, hopefully removing the arguments that the function is not being applied to. But we can also take this partial function representation and turn it into a table of all the arguments that it is defined for and all the results that the function has for those arguments. And then, of course, we can just show that table as a string. So I won't talk about this display function. I think you're well versed in Haskell enough to be able to write that. So I'm going to talk about this type, and I'm going to show you these four functions on that type. So here's the definition of the type. Oh, your head maybe just exploded, but the important thing is that it's a data type with four constructors. And I'm going to talk about each of those constructors. Okay, so the first constructor is table. So what does table do? It takes a list of pairs, and it turns a function, it lists pairs from A to C, and it creates a function, a partial function from A to C. And the idea is that this list is not very large, so maybe it has 200 or 1,000 elements or something like that, of that order of magnitude. If you want more, you should use the other constructors in the data type. And we need equality on A, because we're going to look up in this is a lookup table, right? So we're going to look up A's in this thing, so we better know which A's are equal to the other ones, or which aren't. So that's the first constructor. The second constructor is called pair. I could also call it unpairing. So pair allows us to construct partial functions from pairs of A and B to C, given a curried version of that function. So if we have a partial function from A, a partial function from B to C, then we can turn that into a partial function from pairs of A and B to C. You can see how this works, right? If you have an A and a B, you can just look it up in the first one, and look the Y up in the second one, and the other way around. So that's what the pair constructor is for. So we can construct types that are a little bit more complicated than just flat lookup tables. And then we have the union of two partial functions. So if we have one partial function here, it's defined for some arguments and undefined for some other ones. Another partial function here, I can join them together, and then the resulting one first looks in the left one. If it doesn't exist there, it looks in the right one. If it doesn't exist there, then it says no. Okay. So if we only have these three constructors, we could only construct things of simple types and pairs. And that wouldn't be so nice. I want to construct functions from lists and trees and these kind of things. So I need to be able to convert back and forth from the boring types that I already have two nice types that I would like to have. And that's what this trans constructor does. And I will draw you a picture before I show the type. So what does the trans constructor do? Well, it says, suppose you have a type B and a type C, and you already have a partial function from B to C, or you know how you can make partial functions from B to C. And now you have a new type which is bigger than B, and it's nicer and more structure. Here it is. There it is, A. And I want to make partial functions from A to C, knowing how to make partial functions from B to C. Well, trans says, if you tell me the relationship between A and B, I can do this for you. So, the first thing you tell, so I want to do this, right? The first thing you tell, how to embed B in A. So you give a function from B to A. And I might not reach everything in A, but that's okay. And I also have to be able to go back, so I have to give a function from A to B, which might fail because A is much larger than B. So some of the A's will not have any place in B. Alright? So if I give these two functions, then I can take a partial function from B to C and turn it into a partial function from A to C. That's what this says. Given a normal function from A to maybe B, and a normal function from B to A, so these are just transforming functions. And then I can turn a partial function from B to C and a partial function from A to C. So this allows me to take boring types B and turn them into more nice types A that I really want to use. So those are the four basic constructors. So you might expect to see a constructor like this. You know, the constant function that doesn't look at this argument and just return C whenever you give it. And we can't have that function. And why is that? Because when I look at this partial function, I don't know for which arguments it's defined, or rather, it's going to be defined for possibly infinite number of arguments. And I don't want to do that, because I want to be able to take a partial function and generate the function table that belongs to it. And I can't do that with this constructor. So, I not only have to be explicit about what the results are of the function, I also have to be explicit about what the arguments are of the function all the time. And that's what allows me to do both of these operations. So I can't have this. Okay, I'm also going to assume that there's a functor instance, and it's trivial, so I won't bore you with the details. So what it does, it looks at the result of the thing. So if you have a function that from A to B, it turns it into a partial function from A to C, if you know how to convert B's to C's, and that's fine. That's not easy, not difficult to do. Okay, let's go back to the picture. So, we have these functions, and let's look at the table function, which is really the easiest to understand. And then you can also see what, if you didn't understand some of the constructors, you can see from this definition what they should be doing. So we're going to create a representation of a partial function and turn that into a function table. So here's the code. So there's four cases. Either we already have a small function table and we just return it, or we have one of these pair functions, which is really a curried function. So what do? We create the table for that, getting back the x and another partial function, for which we then create a table, getting back the y, and we find the result, and then we construct the pair x, y, and the result. Okay. So not surprisingly, the table for the pair uses table twice. The union of the tables is just the plus of the, just concatenating the tables. And here I assume that there's no overlap between these functions. And by construction, I'm never going to do this. That's an invariant that I'm going to maintain. And finally, if I have one of these transformers that has one function from A to B, another one from B to A, I'm only going to use one of them because I'm going to construct tables. So I just construct the table for P for the boring type, and then I use H to turn that into my fancy type. Later on I will use the other function that's going the other way. So that's what table is. So this table allows me to show partial functions, if they're finite. Yeah, if these partial functions are not finite, then you never really know what happens in your table, because because if this is infinite, then you will never reach these, but that's okay. So we're only going to use show on finite partial functions. Okay, back to the picture. I will now show you apply, which is almost as easy as table is. Basically, if you sit down and look at the types, and you can see how to do it. So here, again, we have four cases, and I made a little, there's many ways you can do this, but this is the shortest and sweetest way of doing it. So it takes this partial function and a default result, and turns that into a function from A to C. And the default result we use when the partial function is not defined for the A. We could also have made a partial function from A to C to A to maybe C. That would have also worked, but then I would have needed more maybes and more cases in this definition, so I didn't need that. Okay, so just quickly going through this. How do we apply a finite table? We just look up the x, and if it doesn't exist, we return d. So this is idiomatic way of writing that. How do we apply a pair function to a pair x, y? Well, we apply p to x using the default d, and we also apply q to y, where q is the result from p. And I write it like this, so I take the p, which returns a q, and I first use fmap to apply all those q's to the y, and then I apply the result to x. This is, if you don't do it like this, you get a little bit of trouble with type, so it becomes more complicated. You can also first apply p to x and then look at the result, but then you have to construct a default element that has the right type. You don't have to do it in this case. Okay, union is also quite easy. We just apply x to p first and use the application of q to x as the default for that. So if p fails, then we just look at q. And finally, the transformation applied to x, then we actually apply p to x, and then we use, we transform the x with g to something, and if it's nothing, then the result is nothing, then it didn't exist. But if it's just, then we apply p to the result of that. Okay, so we can see here, if we go back to the picture, so table went this way, this is where we use the h of the transformer, and apply went this way, this is where we use the g of the transformer. So both of these parts of the transformer are actually, depending on which way you go. Okay, now we'll talk about the shrinking function. So we have a little intermezzo, that's why the screen becomes green. So, the typical way that shrinking functions in Haskell work is that you have a recursive data type, for example this tree data type, and shrinking takes one of these types that you have, and the elements in the type, and gives you a list of possible candidates that might also be counterexamples, and they should be slightly smaller. But of course there might be an exponential number of smaller trees, so we make sure that this list is not exponentially large by only taking one shrinking step, as they're called, at the time. So how does this work? So this is the typical way that you write shrinking functions over these recursive data types. So if it's a leaf, well then making a leaf smaller is not possible, it's still a leaf, but you can make the element, the argument of the leaf smaller, and we just call shrink recursively, and this is an overloaded function, so this will be the built-in shrinking function for integers. So we get, if you get a leaf of 3, we get a number of leaves that are smaller than 3. How do you shrink a node? Well, if you have a recursive constructor, then we always try to shrink to either the left tree or the right tree first by throwing away the other half. So that's, if that works, then it's really nice, right? Then we have thrown away about half of our argument. But if that didn't work, if that wasn't the counterexample, then we keep the node constructor, but we recursively try to make s smaller. And if that doesn't work, we recursively try to make t smaller. But we never try to make both of them smaller, so we avoid an exponential blow up there. Okay. So basically we're going to apply the same technique to shrinking in our type. And there's 4 constructors, and I will show each of them on a separate slide. And there's one technicality that I had to do, is that, so really I want to have a function that takes partial functions from A to C and returns a list of partial functions from A to C. But I need to also parameterize this with the shrinking function I'm going to use for the result. So this is, given a function that takes the result, type C, to a list of smaller c's, then I can turn a partial function from A to C into a list of partial functions from A to C that are smaller. Okay, so if it's a table, I use the built-in quick check function that shrinks list. It's quite nice. It chops up lists into smaller chunks, and it's quite effective. So I'm using that. It's called shrink list. If it's a pair, then I'm using shrink fun twice. Once for p and once for q. And you can see here, this is why I needed to have the argument that shrinks the result, because if I shrink p, I need to tell how to shrink its result, which is a function table again. So I'm using the shrink function twice. Now here's the union. So it follows exactly the normal thing. I try to throw away completely one of the partial functions, either p or q. I throw them away, and if that still works, it's okay. Otherwise, if that didn't work, I try to recursively either shrink q or recursively shrink p. Okay, and this is the place where we can possibly turn infinite partial functions into finite ones. If we throw away q, for example, if that's the case on the cons for a list, and we didn't need that, then we can throw it away, and then suddenly we have a finite function. And finally, shrinking the transformer, that's just shrinking the thing we're transforming, not caring about g and h. Because that's doing a type transformation, so we don't need to care about that. Okay, so that's how we shrink these partial functions. And so there's only one thing left to talk about, and that's how to take a normal Haskell function and turn that into one of these concrete representations of partial functions. And I would like to give you a nice definition as I did before, but we can't have one definition because we need to know what the type A is in order to do this in a good way. So build is going to be an overloaded function. Okay, so there's a class that I call argument because the argument A, if that's in the class, then we know how to take normal Haskell functions A to B to partial functions from A to B. And I'll show you some instances of this class. So here's a very trivial instance, the unit type. So how do we turn functions from unit to something into a partial function? Well, we just use a table with one element. Easy. But we can also do larger types like word 8, which has 256 elements, then we just do this. That also works. And this is the largest type I built this tables for, so I don't build larger tables than this. Okay, so we can have pairs. If we know how to build partial functions for A and B, then we can also build partial functions for the pair AB. And then, of course, we use build twice again, and on the curried version of f. So f is a function that takes a pair. We curry it first, so it takes an A first and then a B, and then we apply build twice to that. And with an f met thrown in because we want to apply it to the result. And finally, this looks a bit more complicated. This is for the either type. If we know how to build functions, the partial functions for A and B, we can also build it for either AB. And of course, we use union there. And how do we do it? Well, we have the function from either AB, and we decide to only look at the part that works on left, and then we decide to only look at the part that works for right, which are partial functions, of course. So we recursively build them, and then we do some type transformations there, and then we can union the whole thing together. And here we see that we need the maybe type because we use from left and from right, which goes from a larger either AB type to just an A type or a B type. And we need to have the maybe in there to say, no, this wasn't the left, or no, this wasn't the right. Okay, so those are the holy trinity, right? It's unit and pair and sum. So if we know how to do those, we can do everything, right? And this build map function is a helper function that's going to allow us to do that. So what build map is going to do is to say, if you have a function from A to C, I will turn it into a partial function from A to C. If you give me a way of going back and forth between your type A and another type, boring type B, that I already know how to deal with, right? So if we have a boring type B that we already know how to deal with, meaning unit, pair, or plus, and we know a way how to take the fancy type we want to deal with, for example, list, to B and back again, then we can turn normal functions from A to C into partial functions from A to C. And here's the implementation. It uses trans, of course, and it throws in some justs here and there. And you can look at this in the paper if you want. It's not really important. Okay, so here's an example of how we deal with lists. So the build function is just build map of G and H, where G takes a list and turns it into something that uses lefts and rights and pairs. And H is the inverse of that. And here I'm using this isomorphism, so lists are isomorphic to either unit or the pair A, list of A. And the recursion is nicely dealt with in the type class mechanism, so I don't have to do this recursively. And so this is quite standard when you do this kind of type generic programming in Haskell, so I won't bore you with these details. Okay, so we made the partial function type, we made the 4 major functions on it, and so what does the fun type look like now? Well, the fun type, fun AB, the thing we pattern match on, remember, it had the actual function we cared about here as the second argument, and some administrations as the first argument. So what's the administration? Well, it's the partial function that we build, plus the default result that we are going to use if the partial function is not defined. Okay. So when we generate a random fun AB, how do we do that? Well, we generate a random A to B function. We know how to do that. Quick check already knows how to do that. And then we use build to create the partial function. Oh, and by the way, we also generate a random default result. Okay, so that's how we create fun AB objects. And now when we have a fun AB object in our hand, and somebody asks us to shrink it, well, of course, we use the partial function to shrink it. So we shrink the partial function, and then turn that into the actual Haskell function again. And hopefully, the function is still a counterexample. If it's not, then it wasn't a good shrinking step, so we take that back. And the whole point is that if we take an infinite function, it becomes an infinite representation of partial functions. But if it's a counterexample, the shrinking will always terminate and create a finite representation of a partial function, which we can then show. And the show function, of course, uses the partial function as well. So shrink and show never look at the function object, That's only where arbitrary comes from. Okay, so how much time do I have? No, okay. Well, I started 6 minutes late, but anyway. That's fine. So I skipped the final demo, and I have the last 2 slides. So, we get more feedback when testing, and feedback is always good when you have this kind of stuff. And it's sort of, you get it almost for free if you quantify over functions. That's nice. So, if you don't quantify over just functions, but if you quantify over data types that contain functions, for example, you have your favorite monad type that has a function in there somewhere, then you have to do some extra work for this to work. Because you can't just use the functions, you have to turn them into these fun AV objects, and maybe you don't want to do that in the rest of your program, only for the testing, and so there might be some conversion back and forth between the type that you're using in your program and the types that you're using for testing. That's not so nice. I don't really know how to deal with that in a nice way. So there's some extra work involved. So that's a limitation of this approach. Otherwise, you can try it. It's on Hackage. And actually, this has been a standard module in QuickCheck for some time, but I cleaned it up and I wrote a nice paper about it because I never told anybody about it. So now I have. So thanks.